Tonight's presentation, Project GADfly Update. Our presenter, Mike Bush. Mike is president of Savvy Aviation Incorporated. He's an author for numerous aviation pubs, holds a CFI certificate, AMP certificate, IA privileges, Aviation Maintenance Tech of the Year with the FAA going back to 2008, and an EAA member. Mike, thanks for being with us tonight. I'm turning control of the presentation over to you.
Well, good evening, Tim. Good evening, everybody. What was the about?
An interesting title, and the GADfly word in my mind is very interesting. So I'm
Okay.
interested
Well,
to hear what we're all going to hear.
it is an interesting subject. So, at any rate, let me get started here. I think everybody can see my presentation. Project GADfly is probably the most ambitious effort that my company, Savvy Aviation, has gotten involved in terms of AI today. We've done a bunch of stuff with AI. We've got a bunch of AI projects in the hopper. I'll talk about a couple of them later. But for a long time we've been analyzing engine monitor data, looking for signs that exhaust valves are burning and stuff like that. It's a project called FIVA that we've had deployed now for probably 3 years. But GADfly, which we've been working on for about the last 2 years, and is just actually going live. Went live a couple months ago. Is the GADfly, the GAD stands for Generalized Anomaly Detection. And this is an AI model that we have developed, whose purpose is to analyze engine monitor data as it's uploaded and look for anomalous data that we think somebody ought to take a look at. Savvy's been doing engine monitor data analysis since 2010, so it's been about 15 years now, and in that time we've amassed a database of about 9 million flights of piston GA aircraft, with about 10,000 new flights being uploaded each week. So it's a very busy platform. And with 10,000 new flights being uploaded each week and our analysis team being about 10 people, we obviously can't look at all of the flights that are uploaded. And so, which flights should our analysts be looking at out of these 10,000 flights that are uploaded every week? And in the past, they basically have looked at flights that the aircraft owner who uploaded the data asked them to look at, and usually because the aircraft owner thinks something might be wrong, the engine hiccuped on the last flight, or he had a high CHT or something, and he wanted us to look at it. But typically our analysts only look at flights where the aircraft owner has asked us to look at the flight. But we wanted to see if we could do something a little bit more proactive than that, and look at problems that the aircraft owner didn't even know he had yet. So the idea of generalized anomaly detection is to look at a whole bunch of flights and try to identify any where something doesn't look right. And how do you do that? Well, it turns out to be very complicated to do that, but conceptually it's fairly simple. And it takes a little effort to understand or visualize what's going on, but this is a very simplified depiction of what we're doing. The engine monitors in these airplanes typically grab readings from a whole bunch of sensors. Can be 20 or 30 sensors. All the CHTs, all the EGTs, oil pressure, oil temperature, all sorts of air data stuff. Sometimes fuel quantity, just fuel flows, all sorts of stuff. Anything they can get a sensor on. And they sample this data. Most of the modern engine monitors sample it once a second. Some of the older ones sample it a little bit slower than that. So each flight consists of a large number of what we call observations, which is a snapshot of all of these sensors taken. We take an observation once a second or once every 2 seconds or whatever the engine monitor is set to. So the idea of generalized anomaly detection is roughly this. If we took each of these observations, let's say there were 20 sensor readings in each observation, and we plot that observation as a point in 20-dimensional space, if there are 20 sensors. And if we run thousands and thousands of flights, and which would be millions of observations, and plot points for each observation in this 20-dimensional space, what we would wind up getting is a 20-dimensional blob. Now it's really hard to visualize 20-dimensional space, so for the sake of this slide, I've pretended that we only have 3 sensors in an observation, so we can plot the points in 3 space. And this is an actual blob that we plotted in 3 space. And we wouldn't ever do it in such low dimensionality, but that's 3 spaces is about all most people can visualize unless they're mathematicians. So in this case, we're plotting values from 3 sensors for each observation. One of them is manifold pressure. One of them is the difference between the highest and lowest EGT, and the third one is the difference between the highest and lowest CHT. We just took that arbitrarily, but we have lots more data per observation than that. But I just picked 3 so we could plot it in 3 space, so it's easy to visualize. So we wind up, getting this blob. In this case, it's a 3-dimensional blob of points, and they tend to cluster. And it turns out that the higher the dimensionality, the tighter they cluster. So a 20-dimensional blob would actually be much more tightly clustered than the 3-dimensional one we're looking at here on the slide. But you can get a pretty general idea of where these points lie. They lie kind of in a cluster. And then there are a bunch of red points that you can see that are outliers, that are away from the blob, and those are observations where there's something funny going on. There's some anomaly, and those are what the model is looking for, is observations that are anomalous, that aren't in the main blob, but are away from the main blob. And the farther away, the more anomalous they are. And if we get enough anomalous points that are far enough away from the blob, we say, hey, this flight is interesting. Somebody ought to take a look at it, because it's just not normal. So that's the concept, where we're training this model on thousands or tens of thousands or even hundreds of thousands of flights for a particular kind of aircraft, and we're creating this multidimensional blob or cloud that represents what's normal, and then we're looking for departures from what's normal. So I hope that all made sense. So the way this thing is implemented is when our analysts look at the flight that's been identified as anomalous by this AI model, in addition to seeing all of the sensor readings in graphical form the way we normally do, they also get to see what we call a GADfly heat map, which is that bar across the bottom of the slide. And the heat map represents essentially the anomaly scores that the GADfly model is producing on an observation by observation basis. So if the observation looks normal, then the heat map is green. And if it's looking abnormal, then the heat map starts moving towards light green and yellow and orange and eventually red for something that's very anomalous. So here's a flight where there was a pre-ignition event, and the number 2 CHT started running away. It got up to about 600 degrees Fahrenheit before the cylinder basically shut down because the piston started to melt. And the GADfly model looked at that and said that's definitely outside the blob. That's definitely not normal, and it identified the flight as being anomalous, and it created this heat map to show what part of the flight it was worried about and presented it to our analysts to look at. Now, obviously, the analysts get a lot more data than just CHTs and EGTs. They get tons of different stuff. But the heat map basically tells them what part of the flight the GADfly model was concerned about and thought that it looked abnormal and somebody ought to look at it. This is a lot harder to do than it sounds, and we've been working on it for a couple of years. We had the good fortune of being able to partner on this thing with a guy named John Sipple, who's a professor of computer science at George Washington University and also has done a bunch of generalized anomaly detection work for Google. And he's been working very closely with Adam Goler, who is our resident AI expert. And between the two of them, he does the theory and Adam does the practice. And between the two of them, they've been working and getting this model to where it looks like it could be quite useful. Initially, we decided to use the Cirrus SR-22 as our initial test bed to train the model on, and we picked the SR-22 for two reasons. One is that we have a lot of SR-22 flights in our database, probably hundreds of thousands of SR-22 flights. And also the SR-22 is unusually well instrumented. It has a lot of sensors. And so and we wanted to start with the highest dimensionality that we could, because the generalized anomaly detection works better the more sensors you have. So we use the SR-22 as our initial vehicle for training and testing this algorithm. So right now, the GADfly model is examining each new flight as it's uploaded, and it's actually only looking at SR-22 flights right now, but we plan to expand that. It identifies flights that seem sufficiently anomalous that it thinks somebody ought to look at them. It automatically creates a ticket in our ticket system so that it will wind up being in the inbox of the analysis team. And it generates a timeline heat map of the kind that I just showed you, so that the analysts, when they do look at it, can tell what part of the flight the algorithm or the AI model is worried about. And I should not have said algorithm, because this is not an algorithmic or programmatic thing. This is a multi-level neural network machine learning thing that has been trained on lots and lots and lots of SR-22 flights in order for it to learn what's normal and what's abnormal. So here are a couple of actual examples of SR-22 flights that the model has kicked out. This one, it flagged an area during the climb phase of this flight where the CHT split was unusually large, and the heat map, highlighted that section of the flight. Here's one where I think the pilot ran a tank dry because the engine quit briefly due to fuel starvation, and then came back, and the model identified that as anomalous. And I imagine an analyst looked at it and said, yeah, the guy ran a tank dry. We probably won't bother him about this one. But it definitely jumped out as being something that was abnormal to have the engine quit because of lack of fuel in the middle of the cruise phase of a flight. And here's another. This is a pretty violent pre-ignition event where the CHT in cylinder number 4 just suddenly ran away, and it was confirmed by an anomalous EGT number 4, and the model caught it as being an anomaly and kicked out the flight for somebody to take a look at. One of the problems with machine learning AI models like this is that frequently they will identify something as anomalous, but when the human looks at it, the humans can't quite figure out what the model was worrying about. So one of the things we did when we developed the GADfly model was to develop in a way that provides what in AI talk is called explainability. In other words, to try to get the model to explain why it came to the conclusion that it did. So if an analyst sees a flight that the GADfly has identified as being anomalous, and it's not obvious why GADfly highlighted this particular portion of the flight, the analyst can do a couple of mouse clicks and bring up what's called a blame analysis that shows which of the sensors contributed to the high anomaly score. In this case, CHT number 4 was 40% responsible for it highlighting the flight as anomalous and so on, so that it helps the analysts understand what the AI was thinking when it decided that the flight was anomalous. So at any rate, we've now turned this on, or we've finished our initial testing phase. We've decided it's good enough to be useful. And so it's presently analyzing every new SR-22 flight uploaded to the platform, which, could be maybe 1,000 a week. And when it sees a flight that it thinks it looks unusual, it automatically creates a ticket for the analysis team to review. Now that we have it working pretty well on the SR-22, and there's still a couple of improvements we want to make to it, but basically it's working pretty well for the SR-22. So we're about to start working on training it on various other aircraft makes and models for which we have a large number of flights in the database. So we'll be training it on the turbocharged version of the SR-22, on various kinds of beach bonanzas, on Vans RVs, probably Cessna 182s and 210s. And we'll basically kind of work down, start with the aircraft make and models that are most populous in our database, so that we have the largest amount of training data. And we have a lot of RVs in our system. Probably the RV might be the second most populous, right after the Cirrus SR-22. So that's going to be pretty high on our list. And it's going to be interesting to see whether we can train one model for multiple dash number RVs, or whether we'll have to have a separate training session for RV7s and RV9s. And we're not sure yet. We have to try it and see. Now, of course, a generalized anomaly detection like this is most valuable if the flight data is uploaded early and often. I mean, ideally, the flight data would be uploaded to the cloud right after the airplane came in from a flight, or at least if it was uploaded on a regular basis, maybe once a week or something. But it turns out pilots are just absolutely terrible about doing that. They very, very seldom will capture the data from their engine monitors and upload it, unless they think something's wrong. If the engine starts running rough or something, then maybe they'll dump the data and upload it. But most of the time, they're not very good about uploading the data. And the whole idea of GADfly is to try to detect anomalies that the pilots aren't even aware of yet. So we've been looking for a long time for a telemetry solution where the airplane would automatically send the data into the cloud every time the airplane came in from a flight, without the pilot having to do anything. And we're finally starting to see some of these. For the last couple of years, there's been a box called AirSync, and an aircraft owner can install an AirSync bridge. I think this works mostly with like Garmin G1000s and stuff that write their data on SD cards, and the AirSync bridge has a cellular modem as part of it, has an antenna as part of it, and it automatically grabs the data from the engine monitor and sends it up into the cloud automatically when the aircraft comes in from each flight. At AirVenture, that just finished, Garmin announced a new product that we've been working with them on for some time now, and they announced it at AirVenture, and it's called Garmin GDL60 Data Link, and it's something that they're installing in all the new Cirrus aircraft and basically aircraft that have new Garmin installations. That not a lot of talk about retrofitting these into older aircraft, but again, the GDL-60 has a cell modem, and it automatically uploads data to the cloud every time the aircraft comes in. And both AirSync and Garmin will, once they get the data, can automatically transmit it to the Savvy platform, so that we can do all of our analysis and our AI stuff on it. For retrofit purposes, Garmin has for some time had a product called a FlightStream 510, which allows their engine monitor stuff to talk to the Garmin Pilot application on an iPad or a smartphone, and then use that device's cellular modem to transmit it into the cloud. This is what I'd call a semi-automatic telemetry solution, because it does require that the pilot fire up the application and make a couple of clicks in order for the data to get sent to the cloud. So it's not completely automatic, but it is a solution that works as a retrofit in a lot of older Garmin installations. But the automatic telemetry, I think, is the way of the future, and hopefully more and more aircraft will be equipped with automatic telemetry, so that their engine data can get analyzed, in as close to real time as possible. So there's a lot of exciting stuff. I don't know about you guys, but it's very clear to me that AI is becoming a really important part of our lives. I do stuff with AI literally every day, not just with airplanes, but just just with living. And it's my goal for Savvy to be on the cutting edge of AI in the general aviation space. So, we presently have a number of different AI projects in various stages. The FIVA is one of the first ones we've done, and it's been operational for quite a few years. It's the failing exhaust valve analytics that scans all of the engine monitor data that's uploaded to us, looking specifically for signatures that would indicate the possibility of a failing exhaust valve. And we want to highlight that early and notify owners that that it would be a good idea to stick a bore scope in that particular cylinder. And these reports go out automatically to all of our Savvy analysis clients. And again, when the FIVA report indicates above average risk of exhaust valve failure for a particular cylinder, the cylinder is colored, orange instead of green, then we're basically recommending that cylinder have a bore scope inspection done at the earliest opportunity. GADfly, like I said, we just turned on stream for the SR22. We'll hope to expand it to more models by the end of the year. That's our generalized anomaly detection thing. We've got another project that is looking very promising, and that is our bore scope image classifier. We started our bore scope initiative at the beginning of 24. We have about 150,000 bore scope images uploaded to our system now, with lots more coming in every day. And the bore scope image classifier is our attempt to create an AI model that looks at bore scope images and identifies anomalous ones. And at the moment, we're just concentrating on exhaust valves because that's the most common reason for cylinder problems. And it's doing a pretty good job of identifying burned valves. It's 90 some odd percent accurate on what we call late stage burned valves. It's in 60 or 70% accurate right now on early stage burned valves, and so we need to train it on more data. Right now, we've only trained it on about 1,200 images, which is a pretty small number in terms of training a machine learning model. But as we're able to train it on more and more images, it'll get smarter and smarter, and I would expect that it won't be long before it does it as good a job of identifying burned valves as our human analysts do. And the advantage of the image classifier will be that it will be able to analyze the image instantly when it's uploaded and give immediate feedback if there's a problem. And finally, we're working on a project that we call Ask Savvy. It's a large language model. It's trained on, like, all my books and all my articles and all of the conversations that the Savvy technical team has had internally and so on, to try to make it as smart about GA maintenance as possible. And we hope eventually we'll be able to turn it on. You'll be able to have a conversation with it and ask it to help you troubleshoot problems and so on. That's in very early stages right now, but with the way that large language models capability has been absolutely exploding. I mean, it's really exponential right now. It's really quite exciting. We think that that this thing will have a lot of promise. So those are the AI things that we're working on right now, and looking for more things. And basically, I want Savvy to be the GA AI leader in terms of at least in the maintenance space. So Tim, that's all I have as far as prepared material, but I'd be glad to answer any questions that I can.
Okay, Mike. Yeah, that is very exciting to be on the cutting edge of this very new technology, and you're using it for general aviation. Here we always think GA is stuck, 80 years in the past with all our planes that were flying in magnetos and whatnot. And here, you're incorporating the most modern cutting edge technology that exists for our
Well,
GA
I
maintenance.
wish we
Pretty
could
cool.
modernize the aircraft. That's a little outside of our
Uh,
capability, but we at least want to try to modernize the way maintenance is done.
is that oxymoron? You're taking 80 or 100-year-old technology and using new technology to analyze if it's working right or not.
Yeah, that is strange, but
Uh,
that's what we're dealing with.
Pretty cool. Hey, John was wondering what fraction of the SR-22 flights are being identified as abnormal. Do you have that data?
Um, I don't really have that data. I was actually talking to one of our developers, and I was sort of asking about that just the other day, and he indicated that the GADfly was kicking out maybe 10 flights a week, but that's the numerator. I don't really have the denominator.
Mm-hmm.
I'm guessing, we might get 1,000 SR-22 flights a week uploaded, and so maybe 1% of them are being identified as anomalous. That's just sort of an order of magnitude. Don't take that number to the bank, but it's on that order. And I have to say that we are getting we're still getting quite a few false positives from the GADfly model, where it's identifying flight as anomalous, and then an analyst looks at it and says, I can't see anything wrong. And the biggest problem we are having, and I think it should be fairly easy to fix, is during transitions, like when the aircraft goes from the climb phase to the cruise phase, or when the aircraft throttles back, for landing. The model will often decide that something anomalous was going on, and I think it should be pretty easy to cure that problem. First of all, we can easily identify the phase transitions, and we could just filter out anomalies that happen right at the phase transitions, or we could just say, anomalies that are shorter than 5 seconds, we won't get excited about, or something like that. So we're working on adding some improvements to try to reduce the false positive rate. It's but that's what makes the project interesting, and it keeps getting better and better. That's one of the great things about AI is it it keeps getting smarter and smarter the more stuff you train it on, and so I have really high hopes for this thing. It's working fairly well now, but it could work better, and we're making some tweaks to try to make it work a little better, and to try to minimize the false positive rate.
Mark wonders, what AI software are you using?
Oh boy, now you're above my pay grade. That's an Adam Goller question. I know that it's something running on on Amazon Web Services, but I honestly don't know the details. That's beyond my level of expertise on this thing. Sorry.
A couple people have asked about like engines. So this GADfly will only look at a cohort of aircraft, or can you also look at a cohort of engines? For example, all aircraft using IO 550Ns.
Well, that's a very interesting question, and it's one that more generally, the question is how broad a swath of aircraft can a single model work on? To what degree do we have to train it on very specific engine and airframe combinations, or can, like I said, could we have a model that handles all the RVs? And we don't know the answer to that yet. As I said, we've just been focusing up to date, focusing on the SR-22 to get that working, and we're right at the point now of starting to work on generalizing it to more, to different aircraft cohorts, and whether it may very well make sense to create a GADfly model that only looks at engine stuff, and so that it could handle a broad swath of aircraft that have the same or similar engines, regardless of what the airframe is doing. But you'd probably have to exclude things like air data and so on, and just focus on the sensors that are involved purely with the engine, and not with anything that's airframe related. But it's an excellent question. We don't really know the answer to that yet. That's one of the things that we need to learn by trying it and seeing what happens.
Dan wonders, is there any value in training for a specific aircraft, or does it only work for a large cohort?
Well, I mean, we can't really train a model on a, if you mean this by a specific aircraft, a specific like N number or serial number, um, it's very unlikely that we would have enough data for one particular aircraft to to train a neural network. Usually, you need at least thousands of flights to do that. But you know, a lot of the stuff that we're working on AI, my hope is that eventually this kind of stuff can move from the cloud into the aircraft itself, which would be really cool. And if we had engine monitors that that had uh, you know some NVIDIA GPUs in it that could do this sort of anomaly detection on the aircraft in real time in flight, um, and train on that particular. You'd start with a model that was trained on lots of aircraft of the same type, but then once it was in the aircraft, it would start learning more and more about that particular aircraft and that particular guy who's flying the aircraft, and would get smarter and smarter about what's normal for that particular aircraft. That's not something that that we can work on now, but I can imagine it sometime in the future where AI moves into the aircraft itself and analyzes the data at that level. The tough part about doing that is that when you move the AI to the aircraft, at least if it's a certificated aircraft, then you wind up having to get the software FAA approved, which makes things quite difficult to do. So I imagine if this does happen, this thing that I have in my mind's eye of having AI stacks in the aircraft itself, it will certainly emerge first in the experimental world where we don't have that big heavy FAA flywheel to deal with, and can put some really leading edge stuff in the aircraft. That's not what we're working on now, but it's I can envision it being something that could happen in the future.
Wow. Daniel's comment, do you remember when Captain Kirk would talk to the computer in the Enterprise and ask for information and analysis?
Well, it's funny you should say that. I drive a Tesla. Okay, I'm on my third Tesla. I'm a big Tesla fan, and as of last week, Tesla's large language model Grok has now been implemented in the Tesla computer. So as I'm driving my Tesla, I can be having a conversation with Grok. Now, this very first release that was just an over-the-air update, I think last week, the Grok that's in my car doesn't yet have agency to do things to my car. I can't ask Grok to change the cabin temperature, or or navigate me to a certain place. I expect by the end of the year we'll be able to do that. They're being quite cautious about having an AI be able to control the car directly, but that's definitely the way things are moving. And I think I'm guessing by the end of the year, the the Grok in Teslas will actually be able to control the Teslas, which will be really, really cool. So I could have a conversation with the AI about which is the best supercharger to recharge the car on my trip down to San Diego or whatever, and then it could actually change the route to route me to that supercharger. It's not there yet, but it's coming quite soon. So we're pretty close to the Captain Kirk thing.
And Daniel's comment is saying, remember when the flight engineer on piston airliners had an oscilloscope that they could use to analyze both ignition systems on every engine for anomalies? Well, you just did away with his job.
Well, we haven't done away with his job until the stuff moves into the airplane, because he was doing it in real time. But
his job went away when the jets came around.
well, it's true, because nothing
Yeah.
ever goes wrong with those things, right?
So Dana wonders, for experimental, have you considered real-time analysis? He says, I use a Raspberry Pi to collect engine data. It would be nice to have in cockpit for analysis. I guess it goes right into what we were just talking about.
Yeah, I think you need a whole lot more compute than a Raspberry Pi to do this stuff. It's quite resource intensive. But the cost of these things and the size of these things are coming down rapidly. I mean, I don't know what the computer in the Tesla, which does self-driving, so it's very sophisticated AI. I don't know what the computer costs. I'm guessing it's a few $1,000. But you could certainly imagine something like that going into an airplane. So a compute box with that sort of horsepower going into an airplane, you could do some pretty cool things with it. Although it'd be a lot easier to do it in an experimental where you didn't have to satisfy the FAA. FAA is, adds 5 years to everything.
Well, remember now we got this new light sport category with the new Mosaic passing, and I would imagine this could be incorporated through a consensus standard thing, and maybe that would be the easier next step for, aircraft built to a standard above experimental at some point.
Well, we would love to Savvy is not in the hardware business, and I don't intend it to get in the hardware business, but we would certainly love to partner with a hardware company that was interested in doing that.
Yeah, that'd be neat.
Vans or somebody.
Exactly. Well, they build the RV-12. They have an SLSA, so. Wow, exciting things to come.
It really is.
It really is. I know. It's so neat to have you there cutting this edge, Mike. I mean, your company is really contributing so much to taking advantage of technology so we can be savvy as owners of aircraft and, maintain more affordably. And it's exciting. Yeah, it really is.
Yeah, it is. I mean, that's why we do it, because it's exciting and it's fun.
Paul wonders, why does GADfly require AI? Couldn't it just use normal math to calculate the distance between each sample and the average sample and look for a large distance?
Like I say, it turns out to be quite complicated to do this, I'm not the AI expert in the company. I'm sort of the chief evangelist in the company, I guess. But I've been in on some of the sessions with Professor Sipple and stuff on this, and as we've struggled to get the model to be useful, and it turns out to be quite difficult. It's not something that you can reasonably do programmatically. It really needs to be done with machine learning. The inference part of it, which is once the model is trained, then taking that model, looking at a flight and deciding whether it's anomalous or not, that probably requires a lot less compute than the training part. And it's possible that when we start putting AI in the airplanes, the training will be done on the ground, and then the model will be transmitted to the airplane, and then the inference part will be done in the airplane with the computer on the airplane.
Dan wonders, I imagine pilot technique may have the data look different. Have you made any progress on tracking data on which pilot was flying a plane flown regularly by 2 or more pilots?
No, we're not trying to do that, and in fact, we don't have the data to do that, because when engine monitor data is uploaded to us, there's nothing in it that identifies who is flying the airplane. But again, if the AI could be moved to the airplane itself, then it would be a lot easier to do that sort of thing. But it's not something we're working on right now. I know there are a lot of fleet operators that are really interested in that. They rent their airplanes out, and they'd like to find out which of their customers are abusing the airplanes. But that's not something that we're capable of doing right now, because we don't get any information about who's flying the airplane. We only get information about what the sensors captured.
Mark says, I'm a savvy subscriber. Will you offer the analysis service with GADfly to customers being able to download and send you the data for diagnosis and preventive maintenance scheduling?
I didn't totally understand the question. I think the answer is yes, but I was a little confused about what he meant. But certainly, if he meant, will GADfly alerts go directly to the aircraft owner rather than to our analysts? The answer is that's our ultimate goal, but we have to get the false positive rate down to be quite low before we would be willing to do that, because we know from our experience with FIVA that if we give an AI alert to an aircraft owner and then it turns out to be a false alarm, they get really upset with us. And so we need to get the false positive rate down to a very low level before we would be willing to have the GADfly alerts go directly to clients without going to one of our guys to look at first. But I think we'll get there. We're just not there yet.
It sounds like you're just still in the development phase of this. It's not launched into customer use at all to benefit from it yet.
Well, I wouldn't say that, but I would certainly say that we're in the beta test phase. We are passing live flights through the model in basically in real time as they're being uploaded. The alerts are going to our analysts every day, but enough of them are false alarms that we're not alerting our clients directly, but algorithmically that we have a human look at it first. And obviously the goal is to be able to provide the alert to the client directly, but we have to get the accuracy of the model a little bit better than it is right now before we'd be willing to do that.
Sure. I assume once the human says, "Oh, we got a problem here," then you contact the customer.
Oh, absolutely, of course. Yeah.
So Neil wonders, would Adding a sound sensor to the diagnosis on bearings and harmonics. Sound sensor. So if you added a sound sensor on the aircraft, it sounds like, would that help in diagnosing bearings going bad or harmonics causing issues?
I've never heard of a sound sensor being used for that. Sound sensors are used for like knock detection and stuff. There are some engine monitors that have vibration sensors, but they don't seem to work very well because the vibration signature of a piston aircraft engine is extremely complicated. There's a lot of vibration to begin with, and the vibration is happening at lots of different frequencies. You know, the camshaft is turning at half propeller speed, and the mag is turning at 1.5 to propeller speed, and it all gets mixed up in a very complicated vibration signature. So, although there's been some work using vibration sensors, it hasn't worked out terribly well for piston aircraft engines.
Paul wonders, do you feed the human created, this is a false alarm information back into the AI?
Oh, absolutely. Absolutely.
Jack wonders, are you looking at this the right way? Question mark. The cheapest current automobile engine is far more sophisticated than a piston GA engine. Wouldn't it be not far better and safer to put auto engine technology in GA engines? Are we missing, not solving a problem with a technological sledgehammer when the most direct and obvious solution is staring us in the face?
Well, interesting question, but for example, if we look at EAB aircraft and we look at the safety record of EAB aircraft, it turns out that the incidence of catastrophic engine failure in flight is greatest with auto engine conversions and is least with certificated aircraft engines, even though the certificated aircraft engines are much, much older designs than the Subarus and the various auto engines that are used in conversion. So again, this is not an area that I'm an expert in, but I've looked at the numbers, and using automotive engines in aircraft has not worked out terribly well. In fact, it seems to me, I seem to remember there was a Mooney, the Mooney PFM, was it, that had a Porsche engine in it, and that didn't work out very well. So,
Andrew wonders, do you think you will train an AI maintenance troubleshooter?
absolutely, yeah, we're working on that. Absolutely, that was the Ask Savvy thing. That we're working on training a large language model to imitate me and our other most senior people, so that ultimately that this generative AI will be able to have a conversation with a mechanic to try to help guide him through a troubleshooting plan to figure out what's wrong with the aircraft.
Well, Mike, fascinating talk tonight. I think it was a good Q&A session. Thanks, everybody. Why don't you take a moment and share your closing thoughts with everybody?
Okie doke. Well, if any of you who are not already on my email list, and we're about to send out some really interesting stuff to the email list that came out of AirVenture. The easiest way to get on the list, at least if you're in North America, is to just text the word SAVVY, SAVVY, to 33777, and you can put yourself on our email list. We send out a monthly newsletter and various e-blasts when interesting things happen, and we actually have a bunch of interesting things that we're going to send out e-blasts on that came out of AirVenture. If you're not in North America, you can go to the savvyaviation.com website, and there's something up at the very top of the page you can click to put yourself on our mailing list. My books are still available on Amazon, Aircraft Spruce, and the EAA bookstore, and they're all available as audiobooks that you can get on Audible if you would like to listen to them on the way to work or whatever. And I do a twice a month podcast with my colleagues Paul New and Colleen Sterling. We did a couple of live podcast recording sessions at AirVenture this year, and they were all standing room only, and we had a lot of fun. But it's a call-in show, so you can get it pretty much everywhere you can get podcasts, Spotify or Apple Podcasts. And if you would like to be on the show, you can send tricky maintenance questions to podcasts@aopa.org, and our producer Ian Twombly will schedule you to be on one of the shows. And finally, the next three first Wednesday of the month webinars that I'm going to be doing. September webinar is titled Ready, Fire, Aim, and it focuses on the importance of doing things in the right order in maintenance, things that are often done in the wrong order, and that's what we'll be talking about. October, the October webinar is back on another AI topic. It's called Borescope Meets AI, where I'll be talking to you about the work we've been doing on an image discriminator, which is now doing a pretty good job of looking at images of exhaust valves and determining whether they're heat distressed or not. So I'll be talking about that in October. And then November, the title of the webinar is Changing the Oil. We'll be talking about why we have to change the oil so frequently in our piston aircraft engines, and things about oil filters and things about unleaded avgas having effect on oil change intervals, and all sorts of interesting things having to do with oil changes, which we all have to do. And so that's it, Tim. I guess we'll see everybody next month.
Well, it sounds wonderful, Mike. Thank you so much. Looking forward to September 3rd then for your next first Wednesday of the month webinar. And to everybody,
I'm really looking forward to tomorrow is it tomorrow? Because I want to learn about the mosaic thing. I was asking lots of questions when I was at AirVenture, but nobody had made it through the 700 pages yet. So I'm really interested in. And that's tomorrow at 7 Central?
7 p.m. Central tomorrow night.
I'm going to try to be there.
Good. Well, we're going to have a full house, so get there early.
Yeah.
There's going to be a lot of people
get a seat in the front row.
Yep, there's going to be a lot of people on. So, well, that's great. Thank you so much, Mike. And to everybody who tuned in, thank you so much for joining us. And as Mike said, tomorrow evening, EAA government advocacy staff will be discussing the mosaic and the new Sport Pilot Light Sport 2.0 rules that we were given during AirVenture. Thanks everybody for tuning in, and have a great night.
Night, everybody.